Ever watch a 4-year-old clean up a playroom? They put the blocks in one bin, the stuffed animals in another, and cars in a third. It turns out some of the most advanced mathematics in the world starts with that exact same logic. In math, we call that bin a set. A set is simply a collection of things that belong together, and the individual toys inside that box, we call those elements. If we look at this box labeled Set A, we can drop different types of collections inside. We could have a box of numbers, like 1, 2, and 3. Or we could have a box of pets, a cat, a dog, and a fish. We can even get specific, like a box containing only even numbers. On paper, we draw the walls of this toy box using curly brackets. When you see these brackets surrounding a list of items, it just means you are looking at the contents of a specific mathematical box. When we move into calculus, we need to be incredibly specific about which numbers we are using. These sets lock our ingredients in place, so we know exactly which pieces are on the table before we begin the actual math. Looking closely at this diagram, we have a large bracket holding the numbers 1, 2, 3, and 4. But notice the smaller set holding just 1 and 2 is nested completely inside it. We call that smaller box a subset. If everything in the tiny box is also in the big box, it's a subset. Now watch what happens when we compare these two sets, 1, 2, 3 and pre 2, 1. Mathematically, these are equal sets. The order is jumbled, but they hold the same exact toys. Sometimes a box has too many toys to list one by one. Instead of writing them all down, we can use set builder notation. Think of this as a magical instruction tag on the outside of the box that says something like, pack all the red toys. We can write a rule to pack a box with all the even numbers. Or we can set a rule to only include numbers greater than 3, or numbers less than 10. The rule does the heavy lifting for us. When we study calculus, we will often deal with functions that apply to millions of numbers at once. Set builder notation allows us to instantly define all those allowed numbers, known as a function's domain, without having to write out an endless list. Here we see two separate collections, set A and set B. Using a command called a union, we dump two different boxes into one giant pile. This is our OR command. We keep everything that is in A or B. And notice how the number 3 just fuses together. But if we use an intersection, we filter out almost everything. The intersection is the AND command. We only keep the specific toys that live inside set A and set B. In this case, only the number 3 is shared between them. Sometimes you'll look for an intersection between two boxes and find absolutely zero overlap. When they share nothing, we call the result an empty set. It's just a mathematical box with nothing inside it. Calculus relies heavily on these exact mixing rules. Whether you are patching broken graphs together into a single continuous line, or pinpointing the exact coordinates where two equations cross paths, you will use unions and intersections to manage the logic. We can map these relationships visually using a Venn diagram. This graphic shows two intersecting bubbles. If we highlight the entire area of both bubbles, we see the union. If we highlight only the overlapping middle part, we see the intersection. Now let's pull these two bubbles completely apart. If we have a box of cats and a box of dogs, they refuse to share any elements. We call these disjoint sets. Recognizing when groups of numbers are completely disjoint helps us track discontinuous functions. Those are the exact moments in calculus where a smooth line suddenly breaks apart and jumps to a new location. Up to this point, we've been sorting separate individual items into boxes, but now we look at the number line. Think of it like a continuous wooden train track stretching out in front of us. We are moving from separate toys to solid, unbroken pieces of track, which we call intervals. Here on our number line is a piece of track marked from 1 to 4. Notice the open holes at the ends. This open interval means we can travel strictly between 1 and 4, but cannot touch the exact endpoints. If we fill those holes with solid pegs, the rounded parentheses turn into square brackets. This is a closed interval. The solid dots tell us that the endpoints, 1 and 4, are now fully included in our allowable track. We can also build a half-open interval. Notice how the 1 is completely solid, but the 4 remains an open hole. That means we include the 1, but we have to stop just short of the 4. Deciding whether to include those endpoints changes the entire outcome of our measurement. In calculus, knowing if a number can actually touch the edge or just get infinitely close is how we calculate the way things change, or the amount of space they take up. As we look down this track, it eventually reaches toward infinity. Infinity is not a specific destination you can ever park a train at. It is simply the endless direction of the ongoing road. Because of that, we can build infinite intervals. This is a piece of track that starts at one specific number, but then blasts off in one direction forever. When you solve a puzzle like the inequality, x is greater than 5, the answer isn't a single number. The answer is a solution set. This visual shows the exact correct interval needed to make the equation true, starting just after 5 and stretching onward infinitely. This brings our toy room together. Sets tell us what specific toys we play with, while intervals tell us exactly where those toys live along the continuous track. Everything you'll learn next is built on these two tools. Calculus is ultimately the study of these boxes and train tracks, only we'll be looking at them through a powerful microscope to see what happens as we move closer to the very edges of those intervals.